So we'll be looking at a few examples on understanding derivatives, right? For each of the cases that we discussed in the previous two videos. So looking at the first case, we're looking at the derivative of the square root of x divided by the square root of x plus 1, right? If we apply the rule of the quotient, right? So when you have the derivative of quotient, if you apply that rule, then in the numerator we'll have the derivative of the square root of x, right? Multiplied by our g of x, which in our case is just the square root of x plus 1, minus our f of x, which is just the square root of x, multiplied by the derivative of g of x, which is just the square root of x plus 1 derived, all divided by g of x squared, which is our square root of x plus 1 all squared. Right, so that's how we apply our quotient rule. Now in the numerator we'll have that what the derivative of let me just write it first as this. If just rewrite the numerator, the denominator as is, because it will come back as it is. So in the numerator, we'll just have the derivative of the square root of x is just 1 over 2 root x. Okay, you can just double check that, and that is multiplied with the square root of x plus 1 minus now the square root of x, right? Multiplied by the derivative of the square root of x plus 1. So now we have this 1 here that's going to just fall away, because when you take the derivative of the 1, you just get 0, right? So we'll focus on the derivative of the square root of x, which we found to be 1 over 2 root x, right? So that's the form that we have. And obviously we can see that 1 over 2 root x is a common factor in the numerator, right? So if we were to rewrite this, we would have 1 over 2x taken out as a common factor. And inside the bracket, you'd be left with the square root of x plus 1 minus the square root of x, all divided by the square root of x plus 1 squared, right? And obviously you can see that the square root of x will just be cancelled with the negative of the square root of x here. And in the numerator, you'll therefore be left with 1 over 2 square roots of x, right? All divided by the square root of x plus 1 squared, right? So let's put a square inside there. And I think you can simplify this further to be equal to 1 over 2 multiplied by the square root of x multiplied by the square root of x plus 1 squared, and that should be the final form that you reach, right? So now looking at the example for the product rule. So we have 2x multiplied by the cubic root of 2x plus 1, and we're trying to find that derivative. So if we apply the product rule here, it tells us that we first have to find the derivative of 2x, multiply that by the cubic roots of our 2x plus 1, plus, right? I'm looking at the general formula here. Our 2x multiplied now by the derivative of our cubic roots. Right? And that gives you what? Well, for the first term, we have the derivative of 2x, which is just 2. That is multiplied by the cubic roots of 2x plus 1, right? Plus, for the second term, we have 2x multiplied by the derivative of the cubic roots of 2x plus 1. And obviously, with the cubic roots here, you have the 1/3 that comes down first, multiplied by the derivative of the inside function, which is our the derivative of 2x plus 1, which is just 2, right? So 1/3 times 2, multiplied by our original function, which is 2x plus 1, but now to the exponents of the 1/3 minus 1, because remember, the square root, the cubic root is just 1/3, right, in the exponent. And this is obviously equal to 2 times the cubic root of 2x plus 1, right, plus, now you will have the 2 multiplied by the other 2 here, all divided by 3, so you have basically 4/3 x multiplied by 2x plus 1 to the exponent of 1/3 minus 1. 1/3 minus 1 is just negative 2/3, right? So you can take that in the denominator, and you'll basically have 4/3x multiplied by the cubic root of 2x plus 1 squared, and the x is there, but you can just put it in the numerator. And yeah, that's the final form. Then next, if you're looking at logarithmic derivatives, then you have our function here, which is e to the x plus x to the exponent of 2/x. Then you will use our logarithmic differentiation, which is what we presented here. Because we have, in our case, if you look at our example, we have one function to the exponent of another. F of x in our case is just equal to, right, e to the x plus x, right? And our g of x, which is our exponent, is just equal to 2/x. And that means that this is just equal to, now, 2/x multiplied by ln of e to the x plus x. Right? And if you take the derivative on both sides, okay, what you have is, on the left-hand side, the derivative of y over y multiplied by, using the product rule, right, the derivative of 2/x multiplied by ln of e to the x plus x And this is multiplied, this is added to 2 over 3, 2 over x multiplied by the derivative of ln of e to the x plus x. And that will just be equal to the derivative of 2 over x is just, since 2 is a constant, you can just take it out of that derivative. So you're left with the derivative of 1 over x, which if you solve it right, you'll see that it's just equal to negative 1 over x squared, right? So that derivative will just be equal to negative 2 over x squared multiplied by ln of e to the x plus x plus 2 over x, right? Multiplied by the derivative of ln of e to the x. If you go back to our original general form for natural logarithm of some function f of x, you have that is just equal to f prime over f of x. So basically equal to the derivative of e to the x plus x. I'll just write that in the derivative form, divided by e to the x plus x. Right, and that will be equal to, if we rewrite it, negative 2 over x squared multiplied by ln of e to the x plus x plus 2 over x, right? So it's 2 over x multiplied by the derivative of e to the x plus x is just the derivative of e to the x plus the derivative of x. And the derivative of e to the x is just e to the x, right? The derivative of x is just 1, so you have e to the x plus 1 divided by e to the x plus x. Right? And I think that's as far as you can take it. So now that you have this, you can multiply by y on both sides, right? If you multiply by y on both sides, on the left-hand side, you're left with the derivative of y. And on the right-hand side, you have this entire thing here multiplied by y. And if you look back at our original supposition, we let y be equal to our question, right? So if you look back at this, didn't write it, but this is what we had. So y is basically equal to our function that we originally given. So you can just substitute that y by its value there, and this is what your final form for the derivative of y is. And even on the left hand side, you can substitute y with its what it's supposed to be. So the derivative of e to the x plus x to the exponent of 2 over x is just equal to negative 2 over x squared times ln e to the x plus x plus 2 to the x, 2 over x multiplied by e to the x plus 1 divided by e to the x plus x, all multiplied by e to the x plus x to the exponent of 2 over x. right? So that's that. Next, if we look at our polynomial derivative and we apply the formula that we given, you have that this, which is the derivative of 3x to the 4 plus x all to the exponent of 12, is just then equal to, the exponent comes down to 12 multiplied by the derivative of the function f of x, which is just the derivative of 3x to the 4 plus x, and multiplied by our function e to the x plus x to the exponent of 12 minus 1, which is just 11. Sorry, 11. And this can be simplified as 12 multiplied by this derivative, and the derivative of 3 to the x, 3 times x to the 4 is just equal to 3 times the 4, which is the exponent, so 12, multiplied by x to the 4 minus 1, which is x cubed. And that is plus the derivative of x, which is just 1, multiplied by 3x to the 4 plus x to the exponent of 11. So this is your final answer for that. Next, if we're looking at the exponential derivative and you're trying to find the derivative of 14 to the exponent of 2 over x plus x squared, you just apply our general form here. So our a is equal to 14, our f of x is equal to 2 over x plus x squared. The derivative of f of x is just 2 over x plus x squared prime, right? Derivative of that, multiplied by ln of a, which is just ln of 14. And that is equal to basically the same thing, but now the derivative here in the middle, you can just replace it by the derivative of 2 over x is just negative 2 over x squared, right? So you can easily show that. Plus the derivative of x squared, which is just 2x, right? Multiplied by ln of 14. So that should be your final form. And now looking at the next one, which is the derivative for trigonometric functions, we'll just focus on an example covering inverse functions. So if you're trying to find the derivative of this inverse function here, this is just equal to, remember the general form that we had for tan inverse? It's just equal to the derivative of the function f of x, which is this function there. That's derived, divided by 1 plus the function squared. And excuse me, that is just equal to In the numerator, if you try to find the derivative of x ln x minus 1, then for the first part, you'll have the derivative of x squared ln x, right? And the derivative of minus 1 will just be 0, so we won't look at that. But if you look at the derivative of x squared ln x, you have a product there. And that will just be equal to the derivative of x squared, right? Multiplied by ln x plus x squared multiplied by the derivative of ln x, right? And this is just equal to copy this. This is just equal to obviously the derivative of x squared is 2x, so 2x times ln x plus x squared multiplied by the derivative of ln x, which is just 1 over x, all divided by 1 plus x squared ln x minus 1 squared, right? So in the numerator, we can simplify further, and we'll have 2x ln x plus x squared divided by x, which is just x, divided by 1 plus the square, the square, yes, of the original function. Now, in the numerator, you can also take x out as a common factor. So if you take x out as a common factor, you're left with 2 ln of x plus 1 divided by 1 plus x squared ln x minus 1 all squared. And that should be your final answer. Right, so thank you so much for watching the video. We looked at quite a few problems here, but this is basically just an introduction to understanding derivatives. That's the whole point. So if you want, just when you're looking at the video, you can stop at any moment and just try to attempt a problem yourself and see if you get to the final answer, right? Otherwise, if you like the video, just give it a thumbs up or something. It might be able to help some other people as well. So just give it a thumbs up and subscribe to the channel so you can have more information and more videos like this if it was helpful. Right. So thank you so much, and I guess I'll see you in the next one.